the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is meant for linear algebra students who are going through linear equations, kind of the earlier content in a linear algebra course, and who should have already learned about or reviewed systems of linear equations, row reduction methods, echelon forms, vector equations, matrix equations, and now you're in the throes of talking about homogeneous systems. And we approach this if and only if theorem right here. This bijection is what we'd call that. The bijection states the following: the homogeneous equation ax equals 0 has a non-trivial solution if and only if the equation has at least one free variable. Now, before going any further, I want to mention something about the language I'm using within this theorem. Now, by definition, really, a linear system is called homogeneous if it can be written in the form ax equals 0. But right now I'm just saying, hey, the homogeneous equation ax equals 0. That is a little bit of leeway that we're going to use with language for the rest of linear algebra. When we say I have this homogeneous equation, we really mean the system of linear equations in the background is actually homogeneous, but this matrix equation, we're just going to go ahead and call it homogeneous as well. It's just much easier to do that rather than saying the homogeneous linear system that is underlying the matrix equation ax equals 0 has blah, 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 right? It's just much easier to say that. So from this point forward, I might use homogeneous equation to talk about ax equals 0, implying there's a linear system in the background that is homogeneous. They're synonymous. Also, this last sentence, the equation has at least one free variable. Well, technically speaking, linear systems have basic variables and free variables. Yet we're looking at a matrix equation. So we're starting to mix language about systems and matrix equations. That's okay, they're actually synonymous, but I'm just letting you know that we're going to start marrying those topics and those definitions together from this point forward. Anyhow, let's repeat the theorem and then let's talk about how we're going to prove it, and then we'll prove it. The homogeneous equation ax equals 0 has a non-trivial solution if and only if the equation has at least one free variable. Now remember, the homogeneous equation always has the trivial solution, so it's always consistent. And because this is an if and only if, you have to prove it both directions. Now, I've had a conversation in a previous video about this, but I'm just going to state it really quickly here. You have two main statements. The homogeneous equation ax equals 0 has a non-trivial solution, and the equation has at least one free variable. Those are our two statements. The first of those statements I will call the statement P. The second of those statements I will call Q. Normally, with theorems, we often see they're written as if P, then Q, and you would write it this way. With bijections, which is what you're looking at here, it's an if and only if. And so you write that as P has this bijection or double arrow Q. It goes both ways. If P is true, then Q is true. If Q is true, then P is true. A normal proof for a theorem like if P, then Q, so like this type of statement right here, requires us to say, well, let's suppose that P is true, and you do some logical deductive work and arrive at Q being true. Or there are other proof methods here that you could use, one being proof by contraposition and another being proof by contradiction. However, with a bijection, you don't just go one way, you have to prove if P is true, then Q is true, and then you have to prove if Q is true, then P is true. So you have twice the amount of work when working with a bijection. So in this proof, I'm going to go ahead and start backwards. I'm going to prove if Q is true, then P must be true, only because I'm going to use a different proof style going forward, if P, then Q. So I tell the world right now, I'm going to prove if Q, then P. And sometimes I just tell that to myself, right? If you're a real mathematician, you're not really telling the world in symbolic notation like this, hey, here's the direction I'm going with this proof. You just prove it and assume that people who are reading your work can latch on to the logic you're using and figure out that you're proving backwards first and then forward second. But for your benefit, I'm going to be very clear about this. So let's go ahead and assume the statement that the equation has at least one free variable. Now we want to arrive at the fact that this homogeneous equation has a non-trivial solution. We already know that it has a solution, and I'm going to write that down. Great, so since this equation is homogeneous, it must have the trivial solution, and this is just using a theorem we recently learned. And that theorem is right here. A homogeneous linear system is always consistent. Specifically, 0 always solves it. We actually use that in the proof. So I'll write that here, that it's consistent. And this is another flexibility in language. Remember, linear systems are generally consistent or inconsistent, but we're talking about a matrix equation. But we all know, wink, wink, nudge, nudge, that really we're talking about a linear system in the underlying background. And so that language elevates to the matrix equation as well. And finally, let's go ahead and look back in our bag of tricks, basically all of our little theorems that we've learned so far, not all of them, but all the major ones. And we're going to identify one of them that's going to be very helpful here. Specifically using the fact that we have a consistent system and that system has a free variable. Now I'm on my critical theorem list that I kind of keep for my students, and we'll see in the text that I use, it's Theorem 2, but it might be different in your text. It's the existence and uniqueness of solutions to linear systems theorem, kind of a mouthful. But we're going to refer to this piece right here. If a consistent linear system has no free variables, then the solution is unique. Otherwise, there are infinitely many solutions. Well, we have a consistent linear system, and it has a free variable. So it's really the second highlighted case. There are infinitely many solutions. It's consistent, it has a free variable, therefore there are infinitely many solutions. So I'll write it this way. By Theorem 2, ax equals 0 must therefore have more than one solution. Now I know I said a moment ago that it has infinitely many solutions, but I don't need all of those solutions. I just need more than one. Because we know that ax equals 0 has the trivial solution. And we just need some other solution. Once we get one more solution, we will have a non-trivial solution. Thus, ax equals 0 has a non-trivial solution. And that is the proof of Q implying P. The equation has at least one free variable, therefore it must have a non-trivial solution. And when I say the equation, I mean the homogeneous equation has at least one free variable, then that homogeneous equation has a non-trivial solution. Some people use a little bracket and shade half of it to let people know what they're halfway done with the proof. I personally don't like to do that, just out of habit, I just don't. I continue forward with my proof without that. So now we're going to prove the other direction, which is if P, then Q. Now this direction I want to be somewhat classy. I want to have a unique looking proof here. The only reason why is because I want you as a viewer to get used to different styles of proofs. And as I was writing down all the possible ways to prove this statement, I found that proof by contraposition was actually the easiest. So to remind you what proof of contraposition is, if you want to prove a statement like if P then Q, that has the same truth table as proving if not Q, then not P. It is the reverse statement with negations, basically. That's contraposition. Those two statements are exactly the same statements, to be honest with you. And the very famous one that gets used all the time, and I actually use it as well, is if it's raining, then it's cloudy. P is the fact that it's raining. Q is the fact that it therefore must be cloudy. If it's raining, then it's cloudy. The exact same statement, stated a different way, but exactly the same. If it's not cloudy, then it's not raining. Those are the same exact statements. And so proving this second statement actually proves the first. That's a proof by contraposition. So let's go ahead and take a look at what we called Q in our statement above, and we'll take the negation of it, the opposite of it. We're going to suppose that the homogeneous equation does not have a free variable. Simple enough of a statement. We want to arrive at the negation of P. That is, we want to arrive at the fact, or the hopeful fact, that the homogeneous equation has a trivial solution and only the trivial solution. In other words, there's not a non-trivial solution. We already know it has the trivial solution because it's ax equals 0. In fact, I'll state that right now. So note, the homogeneous equation is consistent and has the trivial solution. Okay, that's fine. Now remember, we want to land at the negation of P there, that it only has the trivial solution. Well, again, I'm going to go to my faithful and trusty Theorem 2. Theorem 2 tells us if a consistent linear system, which ax equals 0 has a solution, so it's consistent, if it has no free variables, then the solution is unique. That is, it only has that one solution. So the homogeneous system, ax equals 0, has the trivial solution, and because it doesn't have any free variables, that is the only solution. Therefore, there are no non-trivial solutions. I'll summarize that right here. All right, by Theorem 2, ax equals 0 must only have one solution because, again, ax equals 0 does not have a free variable and it's consistent. Thus, 0 is the only solution because 0 is a solution of any homogeneous equation. Hence, there aren't any non-trivial solutions because there's only that one solution. There's no more. So there's no non-trivial solutions, which is the negation of P. P was that it does have a non-trivial solution. The negation is it doesn't. And we have proven that highlighted if not Q, then not P, which subsequently proves if P then Q. So we've proven both directions. Getting used to this proof style, where you're proving if and only ifs, is important as you move forward in mathematics. The next course, if you're choosing to do another course in mathematics, is going to be proof-based, like all proofs. So you really do have to cling to this idea of building logic, clean logic. Notice the entire time I'm trying to encourage you to use definitions and theorems that have been handed to you. That is really the trick to doing good proofs, is to recognize and acknowledge the fact that you've been handed theorems that will drive you through proofs all throughout your mathematical career. The hard part is remembering all the theorems and definitions. Sometimes they're going to be somewhat obscure, so you do have to reach into a big bag of tricks. And sometimes in real detailed proofs and kind of elevated proofs, you have to create your own theorems in the process of building your proof. Now, that won't happen for quite some time if you're going to be a math major, but I'm just letting you know that that's a reality. So getting you used to seeing the logical deductive process is very important. Anyhow, I hope at least the theorem itself is useful. It's an incredibly powerful theorem. In my opinion, a very, very powerful theorem in linear algebra. I use this quite frequently. You're going to reach back, even though this is not named, you're going to reach back and use this every once in a while. So this will be long in my list of critical theorems. In my opinion, that important. All right, enough of me. You guys have a wonderful day, and I hope to see you in a future video. Be good humans.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.